Alright, we're just reviewing this morning to help to see, okay, how much, hopefully you didn't forget over Thanksgiving break, because I know Thanksgiving break was a nice long break, and welcome back to everyone in classroom and everyone by video, but I know it's been a while. So let's go ahead and let's review for it. Alright, go ahead and take out a piece of paper so you can write down stuff you don't know as we get into it, so it will help you kind of jog your memory. If you don't know something, it's okay. It's one reason why we're reviewing is to help you get back into the swing of things, so that way it'll help you as you get going for it. We already took our test last week, so you don't have to worry about that this week. But it's just so that way, okay, since we have learned a little bit new stuff, it'll help you as we go forward to hopefully remember as we're going through. We'll start with Quentin. I don't think I ever start with Quentin. Alright, Quentin, so remember, we've been talking about forces between the atoms in a molecule. Remember, what do you call that whenever it's an attractive force that binds the atoms in a molecule together, like water? Remember what that's called? Starts with C. A what? What? Cation?
What?
Okay, that's an ion that's lost electrons. What do you call like what holds a molecule together? There are 3 different types of this. But what do we just call that? Alright, we'll just go down the line then. Starts with C.
Holds a molecule together. Compound?
Okay, a compound is a type of molecule. Remember, what do you call it? The type of bonds that help hold it together. Or like, what do we call the attractive forces between them?
Oh, I remember.
It's been a while. So like ionic covalent metallic is an example of it, but what is the name for it?
It's there, I see it. Yeah, I think that, but I don't remember.
It's okay. Alright, Chris? No, like, what is that a type of? What do we call that holds the molecule together?
Well, the molecule together
Starts with C.
And covalent, ionic, and metallic.
They're all examples of?
I thought it was covalent.
Alright, write them down. Chemical bonds. So there are 3 different types of chemical bonds. So make a note. There's ionic, covalent, metallic. There's 3 different types of chemical bonds that bind the molecule together. The molecules stick together. Alright, back to you, Clinton. Alright, so what is the rule that says that they tend to react to get those 8 valence electrons? What's the name for that rule?
Optic rule.
Optic rule. Come throw your darts.
Yeah.
Optic reminds me of like, you know the original Spider-Man, Green Goblin, you know the company Green Goblin worked for?
Oh, yeah.
Was like Octave or something?
Something like that.
Something like that if you remember. That worked. I would remember it because Doc Ock had 8 arms. And so Ock worked, so I whatever helps you remember.
Gotta go right.
Alright. Sorry. Alright. So let's see. So there are 3 different types of bonds, ionic, covalent, and metallic. So you have basically a 1 in 3 chances of guessing for it. Let's see, which one is between a metal and a non-metal?
Metallic.
Final answer? Metal and a non-metal.
Yes.
So metallic. Wait. Metallic?
Yes.
Nope. Alright, you can second guess. No! Ionic. It's between a metal and a non-metal. Metal and a non-metal. Try not to touch your face as much as you can, gentlemen. I know it's hard to do with the sniffles, but I gotta keep giving you germs. You can't touch your face because I gotta watch out for COVID. I know it's that season. I know it's that time of year where everyone has the sniffles, and I'm sorry. Sorry, Chris. Alright, so, back over to Glenn. Alright, what type of bond is it whenever it's between a non-metal and a non-metal? Guys, go back. Oh, I forgot to raise up the ceiling. Sorry, Jamie. You're all facing on YouTube now.
Oh wow, okay. Is it right here? Sorry, on YouTube.
Yeah.
I used to have a YouTube channel.
Sorry, Quentin. I don't know why it does that. Hey, there you go.
13. 4.
It's
You want
4.
to say 13?
It's 4. Alright, what type of bond is it between a metal and a metal? That's metallic. So between metals and metals, that's metallic. It'll loop around eventually.
Oh, come on.
I'm sorry. Poor president. Alright, thinking about the characteristics of them now. Which one is characterized by the sharing of electrons? They both want it and they're both hanging on to it. It's between ionic, covalent, and metallic. Give them 1 in 3 chances. Final answer? Nope. Alright, Quentin. Final answer? Nope.
Covalent.
Covalent. Sharing. Both of them want it. So they're going to both hang on to it.
COVID. I was about to land on the 25.
It might slide though. Oh. Alright. Alright, Chris, which one is characterized by the transfer of electrons. One of them gives it, the other one takes it. That's ionic. Good job.
Good.
Alright, which one is characterized by I think of it like a sea of electrons because nobody wants them because they all throw them off. That's metallic, so it's the delocalized electrons.
Fix the string.
Who are you, Audrey?
Yes. COVID.
Sorry, Clinton.
His face.
Every time.
I'm sorry. I'll try to get a new one after the Christmas sales, whenever
So
that
once
is.
he lands, he gets big
You
numbers.
should buy a new board for Christmas.
I try to. Well, keep in mind though, I wait around until like, you know how those toy stores appear in the mall and they disappear like 2 days after Christmas? I go through right after, and that's whenever I get a lot of like my random toy stuff, is I get stuff like this. So keep in mind, they are fairly cheap. That's probably the reason why. I mean, but yeah, they work. So I'll try to see if I can get another one.
What if I bought like a real dartboard with real darts?
I would not hang it up because you know how many dents I get in the wall now in my board.
I have a dartboard.
I would not bring an actual dart.
I have a Star Wars dartboard. I'll bring it.
But it can't use actual darts because I'm not impaling
I
my
have a
wall.
dartboard with
Alright, we gotta keep going. So, alright, Ethan. What holds an ionic bond together technically? Because it's one of them throwing away the electron and one of them taking it. So it's not the electrons really. So what's holding it together?
What's the Star Wars?
I guess a C.
Say the question again.
What holds the ionic bond together technically? Because remember, one of them's throwing away electrons, one of them's taking them. So it's not like the electrons is what's holding them together. So what's holding them together?
Covalent bonds.
Nope. Alright.
Has something to do with chemistry? Is it chemical bonding?
Okay, what holds the ionic bond together? Because one of them's throwing it and one of them's taking it.
Starts with a C.
Starts with C, I guess is the closest I get to it.
Is it like a statement?
Yeah, closer.
Pi.
No, but it is a good statement.
No.
Okay. Alright, write it down. So it's the charges that holds it together, or like the chemical charges or the electric charges. Since one has a positive one has a negative one now, that's what holds them together. Alright. I don't know if I said it this particular way, so I'm sorry, Ethan, back to you, get the harder ones. What's the most important factor determining how atoms form chemical bonds? What are they trying to get?
What's Star Wars?
A number, I guess.
9.
What are they trying to get? Like, what's the most important thing to determine how they're going to bond? What do they want? This is the most important factor.
Wait. No.
You're gonna wait?
No. Mass.
Nope.
I'm throwing out. I don't remember what.
It's been a while. What? 8 what?
8 electrons. You want the octet rule.
Okay, so it's 8 electrons, like what do we call them in the outermost layer?
Valence.
There you go, 8 valence electrons specifically.
You said a number and you said weight.
It's okay. It's okay. Weight
Yeah,
is a
weight
number.
is a number.
It can
Don't
be a
pay.
number. It can be nice.
Just like
Be
age.
nice.
Word.
Hey, oh, well, at least it's tough.
Use a dart don't like her.
I'm sorry. Alright, so.
We'll drop something.
Alright, so whenever we're talking about a covalent bond, if you have a single bond, how many electrons are being shared?
2.
How many?
2.
How many? Sure? Final answer?
1.
1. Final answer? No.
2.
2.
Dang it.
So,
Say 9.
it's kind of like saying a pair of socks. You have 2 socks, but it's 1 pair. Well, it's there. No, it's not.
It's okay, Chris.
I'm sorry. Alright, Chris, if I have a triple bond, how many individual electrons is that? You're going with 3 electrons?
No, say it again.
You
Oh,
were
6.
6. So, yeah. So, think of it like a pairs. Why don't you get your ones on the floor, too, while you're have to do all. Thank you. That worked. Hey, it's there.
Come on.
Ooh, I think we're pumping in the 15 now. Good job. network. There's two in particular that talks about. Because it's a Luma doesn't stick to it.
Covalent network?
Covalent network.
And so,
One of them starts with a D, one of them starts with a Q.
no,
Alright? Give an
One
example of a
starts with D.
covalent network. One starts with D, one starts with Q. I can't give you any more hints about it not being very plain. Alright?
Give me an example of it.
Of a covalent network. So they bond over and over and over again.
Starts with a D and one starts with a C.
One starts with D, one starts with Q.
One is cute, my bad. Is a period like is an element? Yeah.
It's basically, it's made of the same repeating pattern over and over again. One of them has the same type of element over and over and over again, the other one has the same pattern over and over again.
Diatomic?
Okay, diatomic just means that there's two atoms bonded, like there's two atoms bonded together for it.
And it's like some element.
One of them is made up of, I can't give you more hints because Quentin will figure it out for it, and I didn't give him hints for it, but one of them is the idea it's the same element bonded over and over again, the other one is the same pattern over and over again. Like using like a wallpaper.
Distinct?
Nope, not quite. Alright, the two examples for it is a diamond, because it's all made up of carbon
Oh,
bonded over
and
and over,
quartz.
and quartz is the other ones. Those are the two ones for that one. Alright, what do we call, okay,
Where do you find the words
where do you find it?
the nether?
In the game, yes. But in real life, you can find them,
Why do they look
like in
ducks? Why
mines.
do they look like ducks in the game? That's what I wanna know, like white ducks. Am I
Alright,
correct?
back over to you. Alright, do you remember what we call, I think we talked about this very loosely, whenever the electrons are not locked into any one spot with a metallic bond, they're kind of just floating wherever because nobody wants them.
we start with.
Starts with D. It's on this page and then your book re-talks about it later. It's one of the last, I think we talked about it on Friday, so it's literally one of the last things we talked about.
This thing is a
Did you see distant?
Yeah.
Not quite, okay. Alright,
Orphan.
that's a good guess, but no. Alright, delocalized, so they're not local, so they're just kind of just wherever because nobody wants them.
With the word in the book normally.
What?
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 Okay, it's on page 132.
What'd you
Make a note
say?
if you know for it. Alright, what is a characteristic of metals? Because they don't have those electrons locked in, so the electrons are free to move around. What's a characteristic of metals that comes from this?
They don't want their electrons.
What's a characteristic that, like, that you can notice with a metal that doesn't work with like a regular substance? Like, why don't you put, like, your metal spoon, why don't you just leave it in the pot whenever you're cooking? I mean,
Easily.
they melt.
Temperature.
Okay, they absorb temperatures. They're a good conductor of heat. Okay, come through your darts. So, good conductors of heat, electricity, also come you don't stick metal objects in a socket and you don't leave them on the stove.
Wouldn't know if yes.
Why you don't put Pop-Tarts in the microwave?
With the wrappers on, yes.
My brother one time almost burned down our house and broke the microwave because he put a mac and cheese cup in without water.
That'll do it. That'll do it.
Oh, by the way, he's older than me.
Some days people
This
just
happened
don't
2 years
think.
ago.
It's a
2 years ago?
Sometimes-
Alright,
sometimes
isn't he
it
like
just
22 or
happens.
something?
Alright, we gotta go. Alright, what's another characteristic of a metal?
Just is.
There's two words in particular I'm looking for, but if you describe them, I'll take it too.
Hard.
What did Glenn say? He absorbs film?
That they absorb heat and electricity, so he's already gotten both of those.
I never did homework on this.
You remember doing homework a week ago?
Yes, I did.
You guys do homework?
It's more attractive, like more, it's more attraction.
More what?
More it attracts more electrons or something like that.
Because remember, their electrons are delocalized, so nobody wants them. So they're all floating around. What's a property of metals? Because think of it with like making a sword or something. Like, what is like? What about a like for like a regular object?
It's
If I
sharp.
what?
It's sharp.
Okay, yes, but that's not the term. That's not the idea I'm looking for. You'll know in a second. All right, Chris.
Yeah, it turns into can turn from a liquid to a solid.
Okay, not
Is
quite.
that what, like, so when you're making a sword,
Okay, what do you do when we're making a sword?
you melt down the metal,
Okay, and then you do what?
put it into the pattern,
Yep, and then you do what?
you sharpen it
Okay, okay. How do you sharpen it?
with the grindstone.
Okay, between that, whenever you see a person making a sword, they don't just throw it in the mold and that's it, and they don't
They
just sharpen
pound
it.
it.
There you go, you can hammer it into different shapes, and they're ductile and malleable.
So I just wondered.
It was a good attempt.
What was that throw?
It was a good attempt. Hey! Alright, I think that's all the terms we've talked about so far for it.
I was.
Alright,
Yeah.
careful, force that. I don't know if they'll stick based on what the screws are made of.
Bruh.
I'll leave it there for now. Alright, who got 30 or more points?
Hey.
Alright, Quentin, don't forget your candy at the end of 5. Alright, turn over to page 130.
Ethan knows he won because he's gonna get the candy anyways.
No. Alright, turn over to page 136. Let's practice through this a little bit. Alright, we're gonna do just the first one, page 136, number 4. We kind of started this. This is a good kind of review. So, number 4, predict what type of bonding predominates in each of the following circumstances. Let's just do A through D as kind of just like a warm-up for it. So, ASCl3. So, looking at that one, what type of bonding is that? Alright, Quentin.
Ion.
Alright, so AS, remember over here, is a non-metal.
Oh, you
And
got it wrong.
Cl is a non-metal.
Covalent.
Covalent. Alright. Number B, Ethan, which type is that? Lithium bromide.
Oh, covalent.
Alright, lithium is a
Ionic.
metal. There you go. Yes, lithium is a metal. Bromide is a non-metal. So it is something to get going first thing in the morning. I know it's a little bit hard after break. Alright, Chris.
Ionic.
Alright, that's between copper and nickel. They're both metals. Metallic bond. Alright, let's do number D. Alright, so anyone want that one?
Hey.
I like.
Okay, wait, raise your hand. Who wants
I
it?
want D.
Alright, Ethan, raise your hand first though. Okay.
Alec.
Alright, so it's between sulfur and oxygen.
How is it not? Sulfur and
Sulfur and oxygen.
Oxygen's a metal.
oxygen. No, it's not.
They're both non-metals. What type of
Oxygen.
bond is that?
Did you say it was ionic, like between the gases and stuff?
No. Okay. So ionic is between a metal and a non-metal. Covalent is between non-metal and non-metal, and then metallic is between metals and metals. So which one is it?
Well, ionic based up. Covalent.
That is
Start with
covalent.
C.
What?
I was wanting to start with C.
Yep. Alright, so anyone have any questions about doing that? Because you're gonna do the rest of them for homework, but anyone have any questions about how to do it?
Looks
Okay.
like I'm guessing
Moving on. Okay, what do you need help with, Chris? Which ones do you not understand?
everything.
Alright, so if it's between a metal and a metal on the periodic table, which bond is that?
You have to show it out. You have to show it out. You have to work all of them.
All of them? Every
I
single
saw
one of
it.
them? You're in study hall today?
I'm so small.
Oh no.
If we put metallic on all of
We're
them,
gonna do wrong.
Yes.
We're gonna get a whole thing.
No.
Okay.
But I'll just have to. Now keep in mind, if I decide to grade it now, because I'm suspicious of
Alright,
it.
let's do it.
You've never done that. You have never in a million years done
But
that.
if you're acting like I should with the idea of is it a
We're
wonder?
great.
It's like that's a free 100.
You won't.
It might.
You
Might
won't.
seem
I got a
like it.
periodic table in the back of my book. I'm ready.
What you should be using for it? To homework to figure it out. You don't know all the time. You can
You don't
just
know
figure it out
Chris
for
doesn't try on homework.
Alright, let's go ahead and let's get on to page 134 that's talking about bond character. So, your book's pointing out that, okay, most of the time we talk about what bond is dominant because there's very few just pure covalent, pure metallic, pure covalent types of bonds. So, you would point out that a lot of cases there are other characteristics with them, but we speak of it as okay, it is predominantly one type of bond for it. The reason for it has to do with the electronegativity. Anyone know what the electronegativity is? Talking way back, I think in the previous
Negative
chapter.
energy.
Not quite. It's a term used in the textbook with the idea of electronegativity. Anyone remember what that term refers to?
Electrons are negative.
Nope. But remember, all electrons are negative.
Oh, electronegativity. Negative energy.
Nope. Alright? So remember, electronegativity, that has to do with how much that they want an electron. Anyone remember which element has the strongest electronegativity out of all?
Fluoride.
Fluorine. And so that's why that one has the strongest one for it. So fluorine has the strongest one. So your book points out a bond is considered predominantly ionic and the electronegativity difference, or the delta En. So just saying, okay, if the difference in the electronegativity between two bonded atoms is greater than a 7.1. Your book points out that if you go back and if you look at page 126 at the different electronegativity strengths, that the difference between them, if it's greater than 1.7, is considered an ionic bond. Basically, it's between metals and the non-metals. That's sometimes considered to be predominantly an ionic bond. With the covalent ones, with the non-metals, since both of them want their electrons, it's too weak at that point for one of them to take it away entirely. So you don't have to memorize what's the formula to figure this out. No, just know, okay, if it's between a metal and a non-metal, that is, typically it'll be ionic. Then I'm going to use that to figure it out with the semi-metals. Figure out, okay, will the semi-metals, will they lose or gain electrons? Because remember, the semi-metals, these are the ones that they typically start off with 3, 4, 5, or 6 valence electrons. And depending on how they're bonded to another substance, they might decide, I don't really want. Oh my. Okay. They will either decide, I don't really want them, or no, I'll keep them. So it depends on how they're bonded to another substance. Alright, anyone have any questions though about that? But as a general rule, if it's between a metal and a non-metal, it's going to be ionic. Alright, so let's look at the top of page 135. Let's go through these since Chris said he needs more practice. Predict is what type of bonding predominates for the following. Alright, first one, Ag. If you have just a pure bar of Ag, what is that? First off, as a side note, if you have
Argon.
No.
Silver.
Silver, good job. So if I have a bar of pure silver, no, the bar all sticks together, so what type of bond is that? Metallic. Alright, letter B, H2O or water. Quentin, what type of bond is that? Good job, because hydrogen is considered a non-metal. Raise your hand, Chris. Alright, Chris, what's your question? Stop cheating, Chris. Alright, Chris, close up your book. Since you're cheating. Alright, Ethan. So MgCl, magnesium dichloride. Close your book. For real, close it. Alright, MgCl. Alright, magnesium chloride. So magnesium, is that a metal or a non-metal?
Metal.
Metal, so a metal to a non-metal.
Ionic, right?
Yeah, did you say covalent a minute
I said
ago?
ionic.
Okay, ionic, sorry. I thought I heard covalent. Alright, SiCl4. Which one is that, Chris?
So that's silicon chloride.
Good job.
Silicon is metal, semi-metal, right?
Mm-hmm.
Chloride is a non-metal,
Good job.
so it's covalent.
Good job. Now, for that one, your book walks you through how you sell it, but yes, because that one is between a non-metal or a semi-metal and a non-metal, but that one will bond as a covalent. You can take number D as well for it, so FeMg, so it's two metals. Metallic, good job. Alright, anyone have any questions about how to solve those now? Do you have any questions now over your homework?
Can I open my book?
You may open your book. Do you have any questions about of your homework, Chris? Good. Alright, so polar bonds and unequal sharing. Now keep in mind, this is still sharing, so what type of bond is it if they're sharing electrons, Quentin? Okay, yeah, so what type of bond is it? So is it covalent, ionic, metallic? Covalent. So this is getting now specifically into types of covalent bonding as well. Sometimes you have equal sharing where both of them want it the exact same. In most cases though, you're going to have unequal sharing. Somebody wants it more than the other one. We call this we call this a polar bond whenever it's unequal sharing. Your book points out though a covalent bond in which both atoms share equally, that is called a non-polar bond. So if I have oxygen bonded to oxygen, does one oxygen atom want it more than another oxygen, Quentin? I'm sorry. Ethan.
So. Sorry, I didn't hear you. Sure.
Does one oxygen want electrons more than a different oxygen? No, they want them the same. So it's like an equal share. It's kind of like in tug of war, but they're both pulling in equal streams. It's not moving anywhere. Both of them want it the exact same. That is a non-polar bond. In most cases though, because you have two different atoms bonded together, like in a compound, you're going to have unequal sharing. Somebody wants it more than somebody else. That's called a polar bond. This is an example of a polar bond. This is with hydrogen chloride. So this is chlorine, this is hydrogen. Now, between those two, who wants it more, Quentin? Chlorine. So chlorine wants it a lot more. So chlorine just to pull it a little bit closer to they're sharing. It's kind of like watching 2-year-olds share. If you've ever watched young kids share toys before, they're sharing technically, but one of them is typically always going, these are all mine. we're sharing, you have to share with me. And there's typically one little kid that's doing that. Raise your hand, raise your hand, raise your hand, yes.
In case you wanna jump off the app after that.
I'm sorry, you don't have to do it. Alright, so this is one of the reasons why there was unequal sharing. Your book kind of gives you the diagrams at the bottom, and I have a couple of moving diagrams to help you visualize it as well for it. So, wait, raise your hand.
Are they over exaggerated?
Yeah, because they're always over exaggerated. This first one is a non-polar one. So, this is non-polar or equal sharing for it. I think they're showing you just two chlorines bonded together. But it's the idea that they have equal strength or equal pool. So because of that, the electrons move between them equally for it. So this is non-polar. Neither one of them is stronger. If you have a polar bond, one of them wants it more, and so because of that, they get pulled closer towards it. This is again chlorine and hydrogen. And so it's just showing you that, okay, since chlorine wants it more, the electrons get shifted over because chlorine's going mine. Now, if you have a bunch more electrons over here, what partial charge will you develop? Anyone think they know? Raise your hand. Raise your hand. Alright, Ethan?
Negative.
Negative. And so that's what it's also talking about on this page as well, and it's showing you in this diagram that you're going to have a partial negative charge. Now, we use this weird kind of funky looking G down here at the bottom to help show that. It's the lowercase delta is how that symbol is technically called. Does anyone know? Yep. Now keep in mind that it's the Greek letter delta. I can't draw it very well, but it looks kind of like a weird looking symbol for it. But that's the lowercase delta. Anyone know? Anyone know what capital delta looks like?
A D.
Nope.
A triangle.
Yeah, it's the triangle one. So this is the lowercase version.
I said it.
So we use this one, the lowercase version delta, and we'll give it a negative sign or a positive sign to help symbolize. Okay, here is the symbol for it. Now, chlorine in this example is developing the partial negative charge for it because it has the electrons are pulled closer to it. While the hydrogen would develop a partial positive. Now keep in mind, it's not a full positive because it's not the electron has not been ripped off from it. It still has it. Still got a hold on it. It's still partly mine. So sometimes it's still, okay, I have a partial positive charge, but it's not a full one because I haven't lost it yet. So that's the reason why for it. Alright, anyone have a question about that? With the idea of partial charges or with the idea of polar bonding? Alright, we call a molecule like this. We also describe it as a polar molecule because of the bonds. We also call it a dipole. Does anyone remember what does di mean? Two. So, and now, if you're thinking about it with poles with magnets, what does that mean?
A straight rod.
Okay, and what do we call it in magnets?
Negative and positive.
We don't really call it negative. We don't really call it negative and positive in magnets.
Polars.
Okay, poles. So you have not only a negative pole and a positive pole. What do we describe as you think about it, like with the Earth?
Oh,
North and south. So it's the idea of top and bottom or north and south. So we just use that terminology. Now it's the same idea, but yeah, it's north and south for it. So it's okay. So that's the idea of a dipole molecule. There's two regions for it. So this molecule would be known as a dipole molecule for the focus, Chris. So that way it's the idea of it has two regions. It has a partial positive and a partial negative region. So we would also call it a dipole molecule because it has two sections or two partial charges for it. Alright. Your book points out as well. That sometimes we use a special arrow to help represent this. Like, for example, I gotta stop moving chalk already. If I were to draw it like this, with the hydrogen bonded to the chlorine. Now keep in mind, this is still covalent, so how many electrons are being shared here? What?
One.
Okay, so it's a single bond, two. So because of that, now which one's stronger, the chlorine or the hydrogen? Chlorine. So sometimes we'll draw an arrow like this, just being like, okay, both of them still have it, but they're being pulled closer to chlorine. This is a nice symbol because not only does it help show that the electrons are being pulled closer to chlorine, but this one, hydrogen, also develops kind of a partial positive. So this kind of looks like a positive sign as well. So that's another reason why scientists will use it that way for it. Your book points out another example is between carbon and oxygen. So they share though they have a triple bond between them. So, does anyone remember how many electrons are being shared? Raise your hand, Chris. Okay, Chris. Six. Now, who wants it more, carbon or oxygen? Oxygen wants more. Raise your hand, Ethan. Alright, Ethan.
Oxygen.
Oxygen. So, because of that, you would draw the arrow like this.
I feel just like.
Raise your hand. Raise your hand. Okay.
I feel just like carbon. Completely sad. Look at the face you drew. Can you put it here on
No,
please?
no, gotta go. Alright, anyone though have any questions about this?
Oh, I see.
I know, I already saw it. Alright, let's look over at the top of let's look over page 136, number 5. Let's just practice with these as well for it. So tell whether the bonds between the following atoms are polar or non-polar. So all of these are covalent, that's not what it's asking. But if I have silicon bonded to silicon, is that equal sharing or unequal sharing? Alright. Alright, so would that be polar or non-polar? What? Non-polar, good job. So that section's easy. So hydrogen and oxygen, Ethan, would that be equal sharing or unequal sharing?
Unequal.
So that'd be polar or non-polar?
Polar.
Polar, who wants it more, oxygen or hydrogen?
Oxygen.
Good job. Alright, carbon and hydrogen, Chris. So, is that,
Unequal.
what?
Unequal.
Unequal, so it'd be polar or non-polar?
Non-polar. Polar.
Polar. Alright, anyone have any questions about that idea?
Where exactly are we?
It's at the top page, 136, number 5. Alright,
Is
so,
that part of homework?
what?
Is that part of homework?
Yep,
Keep going with homework.
we gotta keep going. Alright, anyone have any questions about this so far?
With the number 5,
Okay.
we just have to say whether it's polar or non-polar.
Yep.
Nothing else.
Yep. Because all of them, because keep in mind, if it's sharing, what type of bond is it?
I just looked at this. I literally just looked at this, non-polar.
Okay, if it's sharing, so I'm not commanding metallic, which type of bond?
Oh, if it's sharing?
Sharing.
What type of bond?
Which type of bond?
Ionic?
Yes, you did.
Covalent?
Covalent! I know it's Monday, I know it's been a long break. Alright,
My
so,
brain is literally still at home right
I'm
now.
convinced you ate your brain off that too.
it's okay. Alright, so, looking at the next section, your book talks about shapes and properties of molecules for it. So, this is getting into how the molecules and how they bond to each other. So, a Lewis structure, your book talks about this already previously with the idea of a single atom. What is a Lewis structure, Quentin?
Yeah.
So if I were to draw a Lewis structure of carbon, how would I do it, Ethan?
Dots.
Alright, so I put C in the center for carbon. Now how many dots does carbon get?
6.
You sure?
Mm-hmm.
How many does it start with?
What is a guess? 4.
4. So I draw 1, 2, 3, 4. Or you can just draw them all the way around. Either way is
I
fine.
was
I'm not gonna
guessing.
get that picky over it. Alright, so if I were to draw the Lewis structure for bromine, how would I draw it, Chris?
Where's bromine?
Bromine is
Just
in number
guess.
7.
I'm assuming we draw 7 dots.
No, what goes in the center?
Battle Royale. PR.
Good job. And then yeah, you're right, get 7 dots around.
That's an R.
This is an R today.
Yeah, that's a,
Alright, so you remember though, okay, Lewis structure, they want us to draw it though and how they bond into a molecule. So this is not just the same idea as, okay, we're not talking about individual atoms, we're talking about, okay, how do they bond all together for it. So, if I were to talk about okay,
no.
sorry. So, if I were to do this, how would I draw, don't scratch my head. So, whenever you're looking at this one, how would you bond for it, or how would you draw it bonded as a Lewis structure? Now, keep in mind, you have to keep everybody happy because what's the rule that says they want to get 8 valence electrons? Right? Alright, Chris?
Octet rule.
Octet rule. So, keep in mind, you can't just pull out electrons out of nowhere. You have to look to see, okay, how many electrons do I have starting off with, and how will they bond so that everybody's happy and everybody's satisfied. So, carbon starts off with how many? 4. So carbon starts off with 4 electrons. Hydrogen starts off with how many?
4.
Good job. So keep in mind, is hydrogen happy with just its 1 though?
Yes.
Is it?
Yes. No.
No, there is a hydrogen and helium, and there's a couple other sections. They want, because they're so small, they'll be happy with 2 valence electrons. So if it starts off with 1, is it happy? No, it needs another one to be happy. Now, for this one, now hydrogen will each bring over 1, and carbon will bring over 1 as well. So there's 2 electrons being shared between each hydrogen and each carbon. So what type of bond is it if it's sharing first off? Covalent. Now, what type of bond is it? What type of bond is that specifically? Like single, double, triple. Alright, so double shares, how many electrons?
So it's a quad.
So-
Cause there's 4 hydrogens.
Okay, so what type of bond has 2 electrons being shared? Single, double, or triple? Single, so each one has a single bond around. Whenever you say a quad bond like that would be like carbon having 4 bonds between another carbon. Now keep in mind, why do we not see this? Why? Alright, well there's 8 electrons all right here, so why is that not possible? Yeah, that's too much for them. They can handle a triple bond with the electrons being there, but 8 is not doing it. So that's the reason why you want to. Alright, so this is how we draw a Lewis structure for a molecule to show, okay, there's a single bond between each one. Now keep in mind, if there's a single bond, that means that there are 2 being shared between this hydrogen and this carbon. So is this hydrogen happy? Yep. Is this hydrogen happy? Is this one happy? You can have it. Well, is this hydrogen happy?
No.
Why?
Yes, it is.
What?
Because the other hydrogens are happy.
Well, why are the other hydrogens happy then?
Because it has the bond.
Cause they have friends.
Alright, how many?
2.
2. Alright, and then is this hydrogen happy?
Yes.
Good job. Now keep in mind, is the carbon happy if it's sharing 2 with each hydrogen? Ethan.
Yes.
Yes, everybody's happy. So that's one reason why you have to check to see, okay, is everybody happy? Does everybody have 2, or you make it up and stand up and pull it forward because I don't want you to scratch my surface. My floor is new and I don't want to get messed up. So this is the idea of a Lewis structure for a molecule, is to help show, okay, how are they bonding to it and is everybody still happy for it? In some cases, you'll have a structure like this, or it's NH3. Alright, nitrogen starts off with how many? 5. So 1, 2, 3, 4, 5. Now there's 3 hydrogens around it. Now keep in mind, each hydrogen will bring how many to share? Ethan. 1. So I have 1 here, 1 here, 1 here. Alright, is each hydrogen happy now?
Yes.
Okay, we're gonna skip that one. I was gonna go ahead and draw just the lines for that one. So each hydrogen is happy. Alright, what about nitrogen though? Because nitrogen is only bonded to 3 other hydrogens. So is nitrogen happy? Chris? How many electrons did it start off with? 5. And if it's sharing an additional
It's
3,
happy.
is nitrogen. So wait, what? What was
It's happy.
It's happy. Now, you might think, wait a minute, it has 2 unbonded electrons. Doesn't that mess up anything? Nope, that's fine. That's perfectly okay for it to have unbonded electrons. Because each hydrogen is happy and nitrogen's happy, so everybody's happy for it. So, we draw these to showing you, the dots are here, or these valence electrons are here. Sometimes scientists, whenever they make the actual molecules, they won't draw them out, but sometimes you'll see it as they'll draw it like this. Helps showing that these electrons have a negative charge around them, and so they can still affect other things around them. That's the reason why sometimes you'll see models with it drawn like this, but not all the time for it. That's an example of a Lewis structure. The last one your book gives has to do with, well, there's 2 more technically for. So, you have the idea of water. So, water is made up of what molecules as a side note? Quentin. Good, also H2O. So, H2O. Oxygen starts up with how many? Alright. You look up periodic table, it's fine. 6. So oxygen, so how many more does oxygen need to be happy? 2. So each hydrogen comes up, each hydrogen has a single bond, and then the oxygen has 2 sections of unpaired electrons. Now keep in mind, is hydrogen still happy even though it has 2 sections of unpaired electrons? Ethan?
No.
It's not? Yes, it is. Now, keep in mind, oxygen, now, because these electrons are here, that those electrons, they have a slightly negative charge, and so because of that, they'll help push the hydrogen up here though, because these electrons are being pulled closer to the oxygen as well. And so because of that, that's the reason why oxygen has such a weird kind of shape for it, and that's the reason why whenever you have water freeze, it doesn't form up in just a solid mass. That it forms up with the idea of kind of like pockets in between it. This is one reason why if you ever fill up a water bottle completely full up with water and then stick it in the freezer, what happens to your water bottle, Quentin?
Freezes.
What happens though if you fill it up all the way up with water in
Not
it?
all of the freezes, but some of it does. Most
In
of
the
it does.
freezer?
Yeah, put it in the freezer and lock it, it won't freeze, but most of it will.
I've never seen that, unless you have some like special type of keto. Now sometimes though, if you have a specialized, like a pressurized water bottle, it'll do stuff like that. But if you have like a regular cheap, like plastic Walmart water bottle, and you stick it in the freezer and you fill it all the way up with water, what's gonna happen to your cheap water bottle?
Oh, yeah, it'll blow up.
Yeah, it's gonna explode because the water expands. But keep in mind, that's a good thing though. Why is it important that the water expands whenever it freezes?
Cause it doesn't want to be together.
What?
Doesn't want to be together.
Okay, well, it's just how it's bonded up because
You
this
can have it
actually
there for a
causes it.
while.
What?
You can have it there for a little while.
Yeah, no, I mean,
Yeah,
like you've seen it there for like a couple of seconds, it won't automatically
yeah,
freeze for it.
cool.
But now if you leave it there like overnight. Alright, but keep in mind, why is it important that water expands? Because most objects, whenever they go from a liquid to a solid state, they're heavier. So why is it important that water, its solid version, is less dense or lighter than its liquid version? Like, why is it important that ice cubes float in water?
Like important?
Yeah. Okay, think about it this way. If you have a pond up north and it's super cold and the water starts to freeze and the entire top layer of the water freezes, if it was more dense than the water beneath it, what would happen, Chris?
I have no idea.
Okay, if you stick a heavier object in a cup of water, what's gonna happen to like your heavier object?
It's going to sink.
It's going to sink. So what would happen if what would happen if water, if it was heavier, if it sank to the bottom? Like if I have a pond and the
Push
entire,
the water up.
what?
It pushed the water up.
What would happen to all the life, like fish and other animals that lived in the water?
It get gone.
They would die. So God designed it to where, okay, the top layer of water, as it freezes, it stays at the top and it just gets thicker. This is one reason why, if you live up north, you can go ice skating on the ponds, not down here. Don't try that. It's not cold enough for long enough down here. But up north, if you wait, now keep in mind, they go out and they test it as well, because I believe the general rule of thumb is you gotta have 4 inches of ice. And again, I haven't lived up north, but I believe that that's what they say, is you gotta have 4 inches of ice to go out to support your body weight on it, to go ice skating on it. But that's the reason why it stays at the top and doesn't sink to the bottom. It's because of this special structure for it, with how it bonds up as it freezes. That's the reason why. And water is one of the very few exceptions. I think it might be the only one to where the solid version of it is less dense than the liquid version. So that way it'll stay at the top and float. That's why your ice cubes float in water as well. Most instances, if you have a liquid version of lead and a solid version of lead, the solid version is heavier. Alright, any questions about that? Alright, so your book points out another example for it with hydrogen and fluoride. So if you have hydrogen and fluoride together, how many does fluoride turn off with, Quentin? 7. So how many more does it need to be happy? 1. So you would have what type of bond? Single, double, or triple? Single. And then you would have 3 regions of unpaired electrons. Now keep in mind, this is still between 2 atoms. So between hydrogen and fluorine, who wants it more?
Alright.
Fluorine. So if it's an unequal sharing, what type of bonding is that?
Polar.
Polar. Good job. Just checking to make sure. How would I draw the symbol, Chris, to help show that it's a polar molecule? That's what I got from that. Alright, how would I draw it for real? Okay, and Eric, which direction? Pointing towards hydrogen, pointing towards fluorine? Fluorine, is that it?
No,
What else I do?
draw a line on the back end.
That works, but yes, you draw the little plus sign basically for it. Alright, so that's the idea of help show this one. Okay, it's 2 atoms, this one is a polar molecule. Keep in mind, is hydrogen happy like this? Ethan.
Yes.
Is fluorine happy like this?
Yes.
Yep, so it looks a little weird with the idea of it has so many unpaired electrons, but it's okay, that's normal for it. Alright, last one, your book gives us an example for this, is with dihydrogen sulfur. Alright, so like this, how would I draw this one's Lewis structure? Anyone want to take a stab at it? Anybody want to take a stab before I call on Chris, just because?
I don't want to take a step before I don't answer.
Alright, Chris, take a stab at it. Alright, so sulfur's in the center, I'll help you out with that one, and there's hydrogen around it. Alright, so what type of bond will probably be between hydrogen and sulfur? Ionic, covalent, or metallic first? Covalent, and then which one? Single, double, or triple? Single, so each hydrogen is happy. Alright, how many valence electrons does sulfur start off with? Sure? 6. So So there's one here, how many dots do I need to draw? Okay, well, there's one dot here for him, one dot here for him, how many more dots for him should I draw?
4.
4. So it has the same kind of look as water. Alright, anyone have any questions about that? Yes?
Not about that, can I send out one of those?
Yeah. We just don't want it that loud in the video. Alright, we'll go ahead and we'll give you your homework and we'll stop there for it. Alright, your homework for tonight, read page 136 through 139, 136 through 139. Answer on page 136 questions 4E through I, and on 5D through H. It won't take you long, but do work it and do it properly. So number 4, E through I, and number 5, D through H. You're also going to do, wait. We're also going to do on page 139, the concept review, 1, we'll just do number 1. Alright, so to help you out again, Chris, so it's page 136 through 139. Answer on page 136, number 4, E through, I think I said I by accident, that's an L. E through L, and then number 5, D through H, So number 4, Jamie, I think I said I by accident, so E through L. I thought that was a capital I and it's an L. So E through L for number 4. And then on page 139, concept review number 1. Alright?